Schobers on orbifold Riemann surfaces.
Thank you. Thank you for organizers, to organizers for inviting me to give a talk on this conference. So I will speak about how to calculate reverse shifts, because Mike Branoff already gave a talk about this, and he explains how it's related to symplectic geometry, to Fukaya skeleton, or skeleton, how should I say it? Then I don't need to repeat all this. I just give some algebraic machinery how to calculate it. So it might be frustrating for geometers because it's kind of just make everything. You don't need much ideas. You just need to calculate at the end of the day. On the other hand, it might make some of papers of symplectic geometers shorter because Professor Fukaya said symplectic topology.
That was a compliment.
So let me start. So I will start from homotopes. It's kind of purely algebraic construction. Later some generalized homotopes appear. The word is due to algebraists in the beginning of 20th century, or maybe middle of 20th century. So you have some algebra A's, like associative algebra with units. You can produce some element delta there. And you want to produce the new algebra. It's just as a vector space. Well, first it will be some ideal in this algebra. It's a vector space, new algebra B. So some two-sided ideal is a vector space. It's just the same A, but the product of two elements A and B in here is of this new product B is just A delta B.
It's not unital algebra.
It's not unital, right? For that reason, it's just a two-sided ideal, and you just make algebra B. You just add adjoint to unit. Sorry, over some field, okay. B plus. So the point is that under some good conditions on this element delta, this is about gluing T structures in the Recolemont. So let me explain why that. So we should consider the category of B modules and the category of A modules and the category of K modules. And the point is, and I consider derived categories of these guys, which I denote just by D of B, D of A, and D of K. And generalization will be mostly about how instead of K consider some other algebra. So the point is that you have actually, well, first of all, just at the level of algebras, you have two homomorphisms, psi1 and psi2, both from B to A. Psi1, so I mean, now it's unital algebra, so of course the unit goes to unit. So psi I of 1b is just 1a. So to define this homomorphism, we need to just define that on this two-sided ideal B plus, which is a vector space. It's just A, and we define it psi I of A as A. So psi 1 of A is A delta, and psi 2 of A is delta A. So we have two homomorphisms, which means that we can pull back the structure along this guy. So we have from D of A, we have
Also can map to 0, yeah?
Huh?
Also can map to 0.
Map to 0 what?
C3 of A will become to 0.
Yes, right. And this will be homomorphism.
Also from B to A it goes through constants.
Which one?
No, just
Yeah, I better consider it as a homomorphism from B to K.
okay.
Just killing the idea. Right? And so I have three homomorphisms from B, two of them into A and one into K. And so this one I will denote by I. So this will be D of K I all star, just pull back of the structure. And these two guys will be psi1, also pullback of the structure psi2. This is the beginning of what is called recollement. In fact, if you consider adjoint functor to these two functors, I mean left, right, but one, they will coincide. There will be a functor from here to here. And so the point is that well, I hope everybody knows what is recollement. It's three triangulated categories, D1, G, and G2. Some fully faithful functor from D1 to D. The other functor means triangulated categories, exact functors. So there is functor J upper star. And there is adjoint functors to both. And there are some conditions, like for instance, kernel of J upper star is just image of. So this is fully faithful image of I low star. So yes, I low star J. This is J low shriek J and J low star. So J low shriek J low star. These three guys are fully faithful. Yeah, it looks like it's okay. So this is the definition of recollement. Which was introduced by Bilenson, Bernstein, and Denis in their famous book Asterisk plus 100 about curious sheets.
Gaber. It's now
It is
official, yeah, that's a new
in
edition.
the room?
Yeah. No, this is a new edition.
Okay, but I read on the orbifold one. So the reason to introduce this kind of formal story is because if you have T structure here and T structure here, it allows you to construct the unique T structure in the middle for which these two functors are T exact. So given a pair of T structures, the gadget which allows you to extract abelian category from a triangulated one by considering the heart of the T structure, which is the intersection of these two categories. So given T structures in D1 and D2 correspondingly, one can produce, there exists a unique T structure in the middle category such that I low star and J upper star are T exact. So the point is that under some conditions on this element delta, this will be this kind of situation, and moreover, the T structure, the standard T structure here is the glued one from the standard T structure here and standard T structure here. Well, I hope everybody knows that the notations and the situation, the standard case where it appears is the following. If you have a topological space X, assume it's just a complex manifold for simplicity, and Z is some probably singular complex submanifold, and U is, so this is I, this is J, U is the open neighborhood, the complement, sorry, X minus Z. So then you have direct category of sheets on X, which are constructible with respect to the stratification of by these two strata. That this is closed, embedding this is open, and you should consider complexes of sheets on X, say vector spaces with locally constant cohomological strata. So it's called constructible sheets with respect to given stratification with two strata. And then you have this embedding. Here is just locally constant sheets on this Z. So this is I low star. And there is a restriction to the open stratum, which is again to complexes of sheets with locally constant cohomology. So this is a topological situation in which which was modeled by the substrate construction. With the Apostol, we have adjoint functors. And the point was introducing perverse shifts as the heart of this glued T structure. So by definition, perverse shifts on X with respect to the stratification is the heart of the glued T structure. And the heart of any T structure, say this D, is just by definition is the intersection of D less than or equal to 0 centigrade. Though category D was triangulated, this will be an abelian category. And this is some formalism which allows you to extract these abelian categories.
Just on the table.
So the claim is that A is well tempered, delta in A is well tempered, first definition. There's two conditions. One is relatively simple, that A delta A, the two-sided ideal generated by delta is just A. The second condition is that this B plus, oops, no. Visible? And second condition is less.
What's about B plus?
And your second condition, that B plus is projective as both left and right. Left and right Riemann. That's not so explicit. Nevertheless, it's possible to prove it in that space.
Can you repeat the back? I can't see.
Remove the back. Ah.
My back. Yeah, so if A is well tempered, then the claim is that you have this Riemann dk dB dA is Riemann, and the structure is good. And for Riemann you probably don't need it. No, actually you do need it, because even adjoint functors to those two, they should coincide. I mean, left adjoint to psi 1 up to psi 1 low star, and right adjoint to psi 2 low star. They should coincide, and it's only true for this not happening. Yeah, so this the beginning of this story is the joint work with Ilya Zdanovsky. We come to this construction actually when we consider some problems related to discrete harmonic analysis on graphs, but today I wouldn't say about this. And then when we understood this Riemann, then it became clear that it should be applicable to perverse shifts, and that's what I'm going to speak today. And this is a joint work with Timothy Logvinenko. But also based on some joint work with Agnieszka Bodzian, which I will explain. So now, if you, so the point is that the heart of this T structure, that is just modulus over B, is the heart of the good heart for this Riemann. So you see, from this algebraic point of view, we see not only the Riemann itself, but also the glute T structure. The glute is that one, that unique one, which I described there. Right, so now I will speak about this joint activity with Bodenta. And this is about a general picture. So you have a Riemann. So given a Riemann D1, D2, and assume that this category is D1 is the right category over some algebra. Just to fix the picture. C1 and C2. Now it's different. C1 and C2. So we take standard T structure here, standard T structure here. We glue them. We got some abelian category, this heart, and we ask how to describe it. And the idea is to find some projective generator in it. Maybe first I should say about projective generator. So you have a abelian category. And object P in A is called projective. Well, everybody knows it means there is no X from this object to any other object. And generator means, so it's generator, projective generator. And generator means that for any object A, there exists non-zero, there exists non-trivial morphism phi, non-zero morphism from P into this object for any object. Now A will usually be algebra, so let me denote it back. So for any X in A, we have non-trivial morphism from P to X. If you have this kind of thing, then you can, if it's a generator and moreover projective, then you can consider algebra AP, which is in the morphism of this object P. And the point is that whole category 8 is equivalent to the category of modules over this algebra AP. Well, everybody in this room knows this story about triangulated categories. It's a similar story about the abelian category. And the functor is just you take an object X and assign to it homomorphism from P to this object X. So it will be a right module of the AP.
So different choice of just usual Morito equivalent.
Yeah, different choice of projective generator gives Morito equivalent algebra. Yeah, so this whole story will be up to Morito equivalence.
So the category.
And of course, you should specify what kind of categories you consider, so that it would, and what on both sides, what properties of this category and which modules you actually consider here. So sometimes it will be finite dimensional modules, finitely generated, finitely presented, or all modules. It depends whether you consider this A to be big category, which infinite direct sums, or so it's. But in general, you should consider this being true. So it's the way how to control abelian category. Just find their projective generator and calculate its endomorphism algebra, and that's what we will do. So how to find? So we have here a projective generator under this condition. For instance, you can take P to be just C1. This algebra is a module over itself. And here P2, but it doesn't matter for me whether I take it to be this projective generator or not. So assume you are given projective generator in the standard T structure here and here. You glue them, so you actually don't need it to be direct category of modulus over algebra. You can say just in terms that there exists in the heart, there exists projective generator if you want. And then we want to construct projective generator here. First, some analysis. It's not very simple story in general, but under some conditions it's simplified. So assume you do have such a projective generator. He is a projective generator in the glued heart. in these three or now more four co-authors, they actually describe simple objects in the middle, from simple objects here and simple objects in the billion categories here and here. They say first simple objects here just push by I low star, you got simple objects here. But if you have simple object here, you should take so-called intermediate extension, meaning the image of reverse J low shriek and reverse J low star. So when you apply it to simple object, if you take simple object here, then this will be a simple object in the group T heart. Today we discuss how what's going on with projective object. There is no such a general description up to now.
This formula makes sense for any Coulomb whenever you do T structures.
I think so. Just take all simple objects from here, say S1, and take I low star of S1. That's one collection of simple objects in this glued heart, and the other is when you take S2 and take this guy for anything. I think this gives simple.
And P just means I truncate in the glued T structure.
It means take H0 in, for this direct hand, just take H0 in the group T structure. That's the definition of intermediate extensions. All these intersection complexes comes from this construction, taking this.
And it's theorem in general that this is all the simples in the.
I think they prove it there, maybe under some conditions.
Yeah.
In general, yes. Right, now about projective generators. So lemma. I think we need. Yeah, so assume we have projective generator here, and well, I think we also need to assume it's derived Coulomb. We should first say what is derived Coulomb. This means when you have three abelian categories, say A1, A2, and A3, consider derived of these guys. And functors, this is A. So all three categories are derived, and you know, and also I low star and J upper star are derived functors. You know, not every exact functor is direct functor. I mean, if you consider bimodules which give this functors, you can easily see. But assume these both functors are derived. It's kind of an important condition. I guess we need it here, but I'm not sure 100%. Then so lemma is that given derived Coulomb and the projective generator, and at first it's not about. Now, first lemma is just explain what kind of recouloments we actually consider. Yeah, so assume it's derived Coulomb. And assume that J low star is T exact. Yeah, T exact functor between categories with T structures means that it takes D less than or equal 0 into D less than or equal 0, and the same for D greater than or equal 0. So J is for glued T structure, we know that I low star and J upper star are T exact, but we don't know it in general about adjoint functors. So, but sometimes they are also T exact. So assume that J low star is T exact. And sorry, I had to introduce one more notion. Yeah, direct recoil, and I assume again that there is some projective generators. So in A1 and A2. So direct recoil G of A1, G of A2, and you have projective generator in A1, in A2. Then, well, first of all, how to understand this picture? I mean, how to control it? It's controlled by this, say, endomorphism algebra of P1, by endomorphism algebra of P2, but the gluing is controlled by bimodal N. And this bimodal is just our home. I mean, A1, A2 bimodal, and it's just our home from J low shriek of P2 to from I low star of P1 to J low shriek of P2. So you have projective generator here, and then this is I low star, there is J low shriek, and somehow this is the gluing DG bimodal. I mean, it's a complex of A1, A2 bimodals, AP1, AP2. In general, it might have many cohomology, but exactness of J low star and J low shriek is something about how many cohomology this guy might have. And the claim is that...
Is it perfect from one?
I mean, it's a bimodal, it's up to quasi-isomorphic.
Is it a perfect as model of one of algebras?
You can take it, but
Yeah.
somehow properties are not that important. Yeah, I mean, if you want to define that by this bimodal some functor,
Yeah,
and this bimodal actually corresponds to the functor, which is I upper shriek J low shriek.
So it should have some adjoint here.
It's a functor. I mean, in terms of Ricolemont, this functor is a functor from quotient category to the subcategory. So the bimodal corresponds to this functor. And it's actually up to shift by 1. It's the same as I upper star J plus minus 1. It is I upper star of J low star. If you consider the compositions here, they are 0. So there's basically just one functor in Ricolemont which defines the gluing. The DG gluing of this calculus. So now exactness of J low star, it's about cohomology of this bimodal N, HI of N is 0 for I greater than 1. Moreover, it's if only if.
Is it bimodal? HI.
But
It's a complex of
it's
bimodal.
complex.
This is the complex of
It
bimodal.
goes in both directions. A priori goes to both directions.
In both directions. So here we restrict it from the above.
Yeah.
And now, so it's first statement. Second statement is only in one direction. So we have J low shriek, and the claim is that J low shriek is exact. Implies that HI of N is 0 for I less than 0. But the inverse is not in general. It is true if your quotient category is the direct category of vector spaces. And in fact, these two conditions, that HI of N is 0 for I not equal 0 and 1, they are kind of distinguished and important. So if you know that J low shriek and J low star exact, then I'm satisfied. But there's some conditions in geometry. There's some examples when it's not true. For instance, the whole theory of quasi-hereditary algebra is about these conditions. And in a sense, you can think about this homotop story is another point of view on the on this quasi-hereditary algebras, but somehow the gluing iteration of gluing goes in the opposite direction. And what they do in quasi-hereditary algebra, they usually start from quasi-hereditary algebra. I mean, this AP is quasi-hereditary algebra if this was a direct category of vector spaces. And then they reconstruct the structure. And here we want to do the opposite. We want to construct this quasi-hereditary algebra or some more generalized versions of them. And this homotop construction is exactly about this.
Alexei, there's half an hour left for the Riemann surfaces.
All right. You want about Riemann surfaces. All right. All right. So, at least I explain you how to. Yeah. No, I didn't explain you how to construct P. So it's general story. Thank you, Chris. So still analysis. So assume we have this projective generator P. Projective generator in the middle. In the group Q structure. Then under this condition, like this, then you have that I upper star of P is I upper star of P is P1, say. E is projective. And also P2 J low shriek. J upper star of P also is projective. Of course, this is projective in A1, and this is projective generator. So we start from projective generator, and then projective generators in A. And because we have, and moreover, you have short exact sequence, something like J upper star P, I low. This will be a short exact sequence. Well, when these conditions are satisfied. So you see this is projective object. This is projective object P1. This is P2. This is P1. And moreover, you have a short exact sequence. In general, if you don't have these conditions, it's not satisfied. And the point is that even you can, if you assume finite dimensional Holmes and X groups, for instance, then you can reconstruct this P from P1 and P2. It's just universal extension. And more precisely, we have this. We have I low star of P1. So assume you given projective generators P1 and P2, that this guy in the middle is extension, universal extension of I low star of P1 by this J low shriek of P2. P1 to J low shriek of P2 dual space. So you can reconstruct it, as I said, only under those conditions. In topology, these conditions are satisfied when Z in X. I mean, it's mostly about topology, though we do consider it as a complex submanifold. For instance, if Z in X is a divisor. Well, it's known from because of Riemann-Hilbert correspondence. Previous shifts correspond to holonomic modulus with regular singularities, and then you can see these functors J low shriek and J low star are exact. So, so this is general picture. And now, if you calculate endomorphism algebra of this projector P, so assume you have this picture, and you want to calculate this endomorphism algebra AP. And the answer is this, that this AP has first a homomorphism in the in the morphism of the first generator, AP1, surprisingly. It's a quotient, and there is some ideal denoted by I, and this ideal is actually a generalized homotop. Like you see there in this picture, we had, well, the quotient was just K, but this ideal was the homotop. And here is the same. It's true that this ideal is actually a home. It's a home space over. I mean, if you just calculate in the morphism algebra, you can see that this is, well, maybe I just say it's kind of generalized homotop construction.
Sorry, I have some small comment to what you said before. That it's this condition, it's failed topology, we get divisor, but all the language abelian categories, maybe it's spaces are k pi 1 spaces only. Then you get, because in general we have chains and base loops.
That's right. I mean, they should be kind of
K pi 1.
K pi 1, maybe along the strata.
Yeah.
Well, we have more general construction for this projective generator when it's not satisfied, but we cannot at least apply. So, one thing which you might ask here, well, first, it's generalized in the sense that it's actually, instead of, you see, there was just one algebra A, and I think there's some element delta. Now, this A is actually kind of it's matrix algebra, say, of some size over C2, over this algebra C2. And element delta could be understood as a kind of free module of some rank n. I mean, homomorphism of free modules. And you can think about this guy as n. This complex of bimodules could be understood in this way. So delta is basically differential, which defines this gluing bimodule n. And then actually this ideal I consists elements x and I. It's an element in the opposite, it's a homomorphism in the opposite direction. And so you can, it makes sense to consider x, if you have two elements x and y, then you consider x delta y. So x delta y. You go again from here to here. I mean, these two modules are not identified naturally. In particular, this delta makes sense only, I mean, it gives the same story if you multiply it by invertible elements on the left and the right. There is also some homotopy elements which give you the same construction, basically, of the homotop algebra. And that's why it's probably called homotop. So this is general construction. Now I want to apply it to topology. So maybe I said about orbifolds, maybe I today consider only very simple orbifolds. And first I will not orbifold, just here consider, in this picture, consider first U to be a disk, complex disk, and Z is just a point in it, very standard thing, but still I believe it makes sense. I mean, there is was described the category of perverse shifts in this case. So we have a disk and a point, and the complement to the point in the disk is this open set U. So it's very first case which was considered by Berenson and Deligne. Nevertheless, my impression, it still makes sense to consider it. And so we should calculate this gluing bimodal first, and then calculate this algebra. Because gluing bimodal delta gives us the, gluing bimodal should give us this delta. To calculate it, one way is just to separate this. I mean, it's this gluing bimodal, as I said, it's just, well, I said it's I, as a functor, it's just I upper shriek, J low shriek, or you can think in the other way, that it's just a cone of natural transformation from J low shriek to J low star. So this is gluing bimodal of corresponding function. So you need to calculate it. And to calculate this guy, you need to choose some acyclic objects, acyclic to both these functors, J low shriek and J low star. And the typical acyclic object, when you consider, say, constant shift Cu is not acyclic, because U is kind of complicated around this point, around this origin. So good acyclic objects are like this. When you consider constant shift on some, it's called U1. So U1 is acyclic to both J low shriek and J low star. Well, of course, here I mean direct functors. And so you can use you just say, to calculate these two functors, you just cover it by these open sets and calculate this bimodal. And what you get at the end of the day, that this algebra, homotop algebra, so we choose n cuts to cover this U to n open sets. So there will be open sets and their intersection, you will write down resolution, and what you get at the end of the day is that algebra AP, which calculated in this way, is the following algebra. It has n projectors, P1, Pn, corresponding to these cuts. So it's 1, 1 with cuts. And there is relations between them, Pi, well, maybe first I introduced algebra, which I denote by C+. So it's an algebra with these relations. First they are idempotents. So first relation is Pi squared is Pi, and second relation is that Pi Pj is 0 if j is not equal I and I plus 1. So for I we already defined it here, and for I plus 1 it's just a free product. So this algebra, it's not the homotop algebra. The homotop algebra, let's denote it by C. It's in the morphism of that projective generator, which we discussed there. And this project, it's just C with one element Y inverted. And this element Y is the following. First, let's introduce W, which is 1 minus sum of Pi's. Well, up to sign at least. Sum of Pi's. Yeah, there. And then take its power, Y, and power. What is important that this is a central element, and moreover center of this algebra in C++. Center of C++ is just algebra in this Y. This Y has the meaning of the monodromy, but somehow it has more meaning of monodromy than ordinary monodromy. It's a monodromy which acts because it's central elements. It's an endomorphism of the identity functor in the category of perverse shifts on the disk. Well, usually people discuss, after the link, people discuss monodromy on vanishing cycles and nearby cycles, because vanishing and nearby cycles together give you the whole perverse shift. But here you have monodromy which acts on perverse shift themselves. Well, in fact, it's easy to check. As soon as you know description by vanishing and nearby cycles, you can check that there is these two monodromies commute with all the structures. So you do have, so this Y is actually an element, non-trivial element in endomorphisms of the identity functor. But you know from these calculations, it just follows. You just calculate the center. I mean to say, just some formal algebraic calculations allow you to make some consequences, which if you do it with just perverse shifts, it's hard actually to guess here. So W is not a central element. But you see, because we sorry, here I should write C y inverse. So C plus. So we have some algebra C plus, which is this one, and then we have inverted their central element y, and that's how we got this algebra. Modulus over this algebra gives us the perverse shifts on the disk. Now, it has to 15 minutes.
15 minutes.
Okay. Now,
Riemann surface?
is it obvious?
No. I just asked it. Now the Riemann surface?
Riemann surface. Well, it's already Riemann surface, isn't it?
This is Riemann surface.
Yeah, this is the Riemann surface.
Ah, you want to check the book maybe?
Now, first I would like to say something. I mean, because it's, this algebra is finite over this center, say C plus D. You can ask, what is it as a sheaf of algebra over spectrum of Y? Right? I mean, let's consider it's kind of dual to our disk. So we consider spectrum of K of Y. Yes, K of Y. So it's a fine line. Or if you invert, then you have just you remove 0 if you consider spectrum of K of Y, Y inverse. So our algebra C is a sheaf over A1, right, over a fine line, and it's C plus. So C plus is a sheaf over this A1, and we can ask what is this sheaf of algebra. The claim is that this is actually, you should consider here Y to be 1. And the Cy is actually embedded in the endomorphism of the nth power of the trivial of the concept of trivial line bundle, and with the only condition that in the fiber with some matrices with polynomial with coefficients polynomials in this Y, and the only condition is that you have in the fiber of this vector bundle you have some in the fiber over Y equal 1, so let's denote by E. So in E at Y equals 1, you have some vector V, and with C plus, and also at 0. And at 0 you actually have a given flag, a fixed flag. Flag in Y equals 0. And the C plus is actually the following. We require that these two guys, in this point and this point, should be preserved. So this vector should be fixed at this, at Y equals 0, and this at Y equals 1, and this flag should be fixed at Y equals 0.
It's something called order, yeah? Order.
Order is, I think, something with inverted, with some property, like...
It's like Riemann, yeah, Ordnung in German.
No, it's a matrix algebra and it degenerates.
Matrix. But I think it should be like Arzuman's.
No.
Order.
I think it's exactly what
Is it?
order
Okay.
contrasts.
All right. So it's an order with these two things.
Yes, it's exactly.
Fixed flag here and fixed one vector here. But then, I mean, I don't know actually the shift theoretic interpretation of this algebra C plus. It's just part of the calculation. Because we actually not need the C plus, we need algebra C, right? Where we invert this, so it means that we just remove this origin. So this flag we should forget about it, and then we go to C. So it's on the complement to 0, and it just fixed one vector. So this is the description of perverse shifts on the disk with a point. Now I probably prefer to go to orbifold disk instead of more complicated Riemann surfaces. So let's now consider, I mean, the reason why now it's about rock ultimately, we were interested in this disk to understand what is PN function, whatever. It doesn't matter, but it looks like it's interesting by itself. So we again consider disk, and now we assume here, at this point, the origin is orbifoldized, so to speak. So it's the group Z over N in this point, but it's a topological picture. So now the calculation of the same algebra shows the following, that so C orbifold is the following. You have this algebra C, which we had before, And then, if you remember in C, we had this element y, which was invertible, right? So now we add x and x, well, x inverse, x would be enough, extra element x to this algebra, which is a root of, nth root of this y. We already had some root here, w, right? Because y was w to n. But w was not central. We add the central element x to this algebra. X central. So now the claim is that reverse shifts on the orbifold. So disk with zero orbifold z over n. Okay. So we consider this point orbifold point and stratifying point. I mean, in principle, you can consider stratifications and orbifoldizations independent of the rest of each other. So these reverse shifts are modules of this algebra C orbifold. So you see, algebra C is a subalgebra with, and this is well, here again we have this n cuts, and n is exactly this n. In principle, you can take number of cuts which is proportional to n. Here I just assume they coincide because everything, in any way, you got some other algebra which will be Morita equivalent, right? So it will be the same category of C or modules. So what we got here, yes, first it was kind of strange that the central element x appears in this algebra. Even y was strange because you see this formula for y is kind of surprising for me. You just have some cyclic algebra of projectors and you got this y. So here, because this C is constructed by means of this generalized homotop construction, so basically, as I said, in this generalized homotop, the quotient algebra, so this C orbital, is the algebra corresponding to the origin. So it's just algebra K. So this was algebra K of cyclic group. I mean, shifts, equivalent shifts on this point is just modules over this algebra. So this is, sorry, it's an algebra. It's a quotient of the homotop. And the kernel is matrix algebra of K of, actually K of y inverse. I write here small y because this is more like matrix n by n. Because this is really the monodromy, but monodromy acts on shifts on the punctured disk. So somehow you see that this was two-sided ideal in this algebra. You can, from the definition of the homotop, you see that this is a bimodule of this algebra. But as I said, even here we already find some element y in the whole algebra, I mean none of the four, which was act here. And here we also have this element x, which acts like this monodromy on this ideal, but it lies in the whole algebra. And this corresponds to this endomorphism identity functor. So here we have similar story. You have this element x is the following. If you take generator sigma in this group, because this group x, this is also a bimodule of this algebra. So you have sigma acting there on the left and on the right, and that's actually action by means of the matrix sigma tilde, which is permutation matrix. It's 1, 1, 1, and 1 here. And then the claim is that if you take elements x, which is sigma minus sigma tilde, then this is a central element in this this homotop algebra. And then, which I don't really understand how to interpret this formula, but indeed it again means the following, that if you take endomorphism algebra of the identity functor of this reverse shifts on this orbifold on the disk, then there is this element x, meaning again some kind of monodromy. I don't know. Certainly there should be some topological interpretation for this. But I mean to say somehow it's just you calculated stupidly and you got some answers which are not obvious at all from from topological point of view.
Oh, maybe just wrapped foci from just a bunch of rays. Yeah, is it?
Yeah, it should be some.
It will be again like matrix algebra in one parameter.
Yeah, I'm asking why you got some central elements which gives you action of this sigma. I mean, you have obvious action of sigma on this two-sided ideal, but why you have central element which gives this action, which is just an element in this algebra? I mean, even here it's not quite obvious why monodromy acts on perverse sheaves. It's sort of, you should, I mean, perverse sheaf is a complex, right? Of course, every constructible homology of perverse sheaf is constructible, so there is an action of monodromy. But why it acts on the extensions? So you should present your category of perverse sheaves by some complexes, and in principle, some complexes of sheaves. So you should require these sheaves to be already with the action of the monodromy, if you want a natural way to prove it. And here it's somehow this embedding of C in C orbifold. It corresponds actually to what? I mean, this is an orbifold. It's a flat. It's a coarse moduli space of our orbifold, right? You have some coverings, n-fold coverings, which could realize your orbifold. And actually, these perverse sheaves, which appear here because of embedding of C in C orbifold. So this corresponds to the perverse sheaves on the covering and not on the coarse moduli space. All right, now actually, instead of describing what's going on for more complicated, well, first I should say this answer is actually could be understood as a reinterpretation of what Kapranov and Shekman did for the disks in a corresponding paper. It's just the other way to say the same. And for this orbifold disk, it's somewhat more complicated. Now I want to present, I mean, all of this was in order to describe Schobers. So what is the Schober? Schober is a categorification, right? The point is that this algebraic description gives you a very simple way how to categorify all this story. The idea is just take this, some elements in this algebra. Unfortunately, it's not just a basis, if I remember correctly. It's a little bit more than a basis. And present them by functors. And there is some issue which was already discussed, that we should consider adjunction. Some functors should be adjunct. So I'm saying, I mean to say that here actually this is not very difficult to realize this program. And the point is, we just add one extra ingredient to the picture. And this is just some anti-isomorphism of this algebra, given by the formula.
A few minutes?
Yes, just keep on that. Okay, I don't. Well, anyway, there is some anti-isomorphism, let's denote by A, from this algebra C orbifold or just C, and A orbifold from C orbifold into itself, opposite, because it's anti-isomorphism, and is given by, well, you just can say where pi goes. If I remember correctly, it goes to the product of pi plus 1, those which you can take products. I mean, coefficients take cyclically, so go back to pi, and you multiply by y inverse, if I remember correctly. So that's the formula, and here you have an extra element x, right, in this description. So x by this A orbifold, it just goes to, I guess, to x inverse. And y goes to y inverse. So if you have this anti-isomorphism, then it induces you some anti-equivalence of the category of modules. Well, actually, the point is just if you present some object, some element f in your algebra by some functor f, then A of f should be presented by adjoint functor, say right adjoint. And somehow how this picture is enough for categorification, you can see, for instance, what's going from this picture. you see here some cyclicity conditions, some compositions are 0, you will see that categorification, so even for non-orbifoldized disk, is just the following. You have some triangulated category E, which is a categorification of the representation space of the algebra. And you have categories EIs, which corresponds to the images of these projectors. So this is actually, just from what I said, it already follows that this is admissible subcategory, and that if you take EI orthogonal 2n times, as it was in Misha paper, in Misha talk, then it's again EI. That's one condition. So it's kind of 2n periodical. I mean, orthogonal means if you take double orthogonal, it's mutation. So 2n mutations, you come back to original category, subcategory. That's one condition. And but there is another condition, and there's another condition that you should have a categorification of this object Y. And this is just some functor, so it's a functor Y. Let me know if it's still by Y. It's a functor which acts on the whole category, but it takes EI to EI plus 1. Or you can instead categorify W. Because of this form, you can see if this is category or invertible, then this is invertible. So categorification is basically the same. And W, because it has very simple formula, you see it's just used for some spherical functor. So I would like. So and what happens if you instead? So it was non-orbifold that case of the disk, and if it's orbifold, then what you do, you just add this nth root of this functor Y. So this Y is actually X. It preserves all. Sorry, Y. It's W. W who take EI to EI plus 1, but Y is a power of W. So Y takes, I mean, it's an equivalence which takes EI to into EI. And this was non-orbifoldized case. And if it's orbifoldized case, then you should take a root of this Y, which also preserves all this category EIs. So this is Schobers, which corresponds to the disk and the orbifoldized disk. And my last point is an example. Okay, so I have time.
A good point.
I think you're at -3 points.
Okay, 1 minute. Just example from geometry. Algebraic geometry or complex geometry. So you have variety X, you have a divisor D in it, and you consider orbifold on D, on X, so X orbifoldized. Means that you consider orbifoldization of order n along this divisor. The claim is that the derived category of coherent shifts on this orbifoldized disk, or disk, it's not a disk, it's just a variety, and just coherent shifts on a variety with orbifoldization and order along the divisor. And the claim is that this, I mean, you can construct this kind of thing, I mean, non-orbifoldized story for this case. I mean, this category do have all the structure which I said there. That was one example, and now it's category is orbifoldized, but we consider non-orbifoldized disk. I mean, Schober on a non-orbifoldized disk, not orbifold disk. And if you have extra thing, if you have for this X some cover n to 1, which is ramified in this disk, or in other ways, this divisor D in Picard group has some root. There is some L such that there exists L such that L to n is D in the Picard group. So you have a finite covering, and quotient by this covering gives you this. Then this picture gives you orbifoldized disk Schober. This is orbifoldized disk Schober. Orbifold disk Schober. When you do have the covering which realize your, global covering which defines your object. Thank you.
questions?
I don't know, it may be naive question, but this is why the group is means you are always considering orbifold maybe some other action by non-compact group means this can be carried out.
On what?
By non-compact group for say.
Well, first we wanted that all, we consider middle terrestrial, so to speak, which means that all strata should be of even dimension. It's just about points. If you have a point, there is no other action. If you, as soon as a smooth, the coarse moduli space is smooth, there is no other actions except for cyclic. If you want non-smooth, then yes.
So like usual for Schober, it's not related to spherical functor. This one like related to lens space functor or something.
That's right.
How's it related?
Yes. So these are different. When you consider the Schober, it's just different interpretation of the same spherical functor. It gives the same data. It's just a spherical functor. That's correct. And after all,
no
for
lens
different
space.
n,
There's no lens space here. so-
Really?
Hmm?
A priori there is no lens space factor.
lens space.
There's no lens space.
No, the point is that for all n, these algebras are Morita equivalent. So it's just different description of this. Misha said a little bit of this. And just you can vary this n, and still you give you give a bigger category, but the data are the same. It's just one spherical functor. And here you have, for orbifold case, you have a bit more. And yes, answering your question, of course, it's just part of the picture. It's just disk with n cuts, but you can consider more complicated Riemann surfaces, and then you should choose a graph as Misha did there, and then you got the answer for orbifold.
Any more questions? Let's thank Alexei again.